Today I will be laying out a strategy for scaling up the bubble column slurry reactor for Fischer Tropsch synthesis. The strategy I will suggest relies on CFD simulations. The material I will present is contained in a vast number of publications from my research group, and these publications are listed in my Google Scholar profile. There are about 40 to 50 publications, and I'll list here 5 of them that are probably representative of the material I will present. The papers with C describe the technology for Fischer Tropsch synthesis and the choice of the bubble column slurry reactor versus the alternative multitubular trickle bed reactor for the same process. The papers co-authored by Jasper van Baarten, Ioana Urseanu, and Anne Foray discuss the hydrodynamics and scale-up strategies for bubble column slurry reactors that rely on Eulerian simulations using input data based on experiments. This presentation is a follow-up of a series of other video presentations on the related topics that are listed here. These video presentations are available on my YouTube channel. The variety of reactor technologies for Fischer Tropsch synthesis. The video is titled The Rise of Bubbles and Bubble Rise in Liquids. Describe the rise of single bubbles using experimental data and also volume of fluid simulations. The hydrodynamics of bubble column slurry reactors for Fischer Tropsch synthesis is described in my presentation entitled The Fischer Tropsch Synthesis Slurry Reactor Hydrodynamics. The presentation on flow regime transitions at elevated pressures describe the influence of elevated pressures on the flow regime transitions in bubble columns with air-water systems. So I suggest you watch these videos before embarking on the journey on scaling up of the bubble column slurry reactors for Fischer Tropsch synthesis. The next 2 slides show you the photographs of the commercial scale bubble column slurry reactors for FT synthesis that is operated by Sasol in Qatar. Bubble column slurry reactors are used by the Sasol Corporation in Qatar for Fischer Tropsch synthesis. Here is a photograph of the bubble column slurry reactors that are being shipped to Qatar. Gives you a indication of the sizes of the slurry reactors used for commercial operations. Here's another photograph of the Fischer Tropsch slurry reactor being lifted by cranes for installation on the site in Qatar. Again, this gives you a good indication of the large sizes of the bubble columns that are used in commercial practice. Before we delve into the bubble column hydrodynamics, let's get a feel for the operating conditions for a Fischer Tropsch slurry reactor. Typically, the gas velocities entering the FT bubble column slurry reactor are in the range of 20 centimeters per second to 40 centimeters per second. The reactor dimensions are shown here approximately. The column diameters may range from 6 to 10 meters in diameter. The column height could range from 30 to 40 meters. The bubble column slurry reactor for FT synthesis operates at pressures ranging from 30 bars to 40 bars. Another important factor that is important for the bubble column hydrodynamics is that the syngas entering the reactor suffers a reduction in the volume because the syngas is converted to hydrocarbons. So there is about a 60% reduction in the volumetric flow rate of the gas as it passes up the column. Due to the extremely high heat of reaction, the reactor has cooling tubes installed in it in order to remove the heat generated during the exothermic FT reaction. Typically, the cooling tubes are about 50 millimeters in size, and to give you an indication of the intertube spacing, I show here a mock-up reactor that was used to investigate the bubble column hydrodynamics. This gives you an indication how close the cooling tubes are. So another factor that needs to be taken into consideration is the influence of the presence of the cooling tubes on the bubble column reactor hydrodynamics. So the key question we address in our presentation is, what is the flow regime under which the FT reactor operates given these set of conditions? It's important to note that the catalyst used for the Fischer Tropsch reactor is in the range of 40 to 50 micrometers, and the catalyst concentration is about 20 to 35 volume percent based on the liquid phase in the reactor. So it's a highly concentrated catalyst within the liquid phase in the FT reactor. So we ask the question, how is the hydrodynamics influenced by the superficial gas velocity? How is it influenced by the properties of the liquid? How is it influenced by the catalyst concentrations? To address all these questions, my group at the University of Amsterdam conducted a comprehensive set of investigation of the bubble column slurry reactor hydrodynamics. The findings are all published in the literature as evidenced in the publications on my Google Scholar profile, and I show you some video animations to illustrate some key points of the bubble column slurry hydrodynamics. This slide shows a schematic of the scale-up strategy I am suggesting for the bubble column slurry reactor for Fischer Tropsch synthesis. The design of the commercial reactor is the ultimate goal of the scale-up strategy. And as is apparent in the foregoing 3 slides, the commercial reactors are about 10 to 20 meters in diameter and could have heights ranging up to 40 meters. The reactor has gas dispersed into a slurry phase, and the slurry phase consists of the oil products along with suspended catalyst particles that could be as small as 50 micrometers in diameter. The dispersed gas bubbles rise through the liquid. There is a range of bubble sizes, large bubbles and small bubbles coexisting, and the bubble rise within the reactor results in liquid circulations. The flow is up through the middle and down the sides. The highly exothermic Fischer Tropsch reaction requires the use of cooling tubes, and we have vertical cooling tubes present in the reactor. Now, this is perhaps the most complicated reactor on this planet from the point of view of scaling up. And the scale-up strategy needs to be very systematic and thorough in order to ensure that the reactor, when operated on a commercial scale, meets with the desired conversion and selectivity targets. The scale-up strategies involves process studies on a, say, micro reactor scale to study the kinetics, catalyst deactivation, catalyst preparation studies. In addition, we need to understand the hydrodynamics of the bubble column slurry reactor. For this purpose, a lot of the hydrodynamics could be studied in cold flow experiments, and such cold flow experiments could provide information and insights into bubble hydrodynamics, mass transfer, influence of high pressure, axial dispersion, back mixing, heat transfer, effect of concentration of catalysts on reactor hydrodynamics. The information on the bubble column hydrodynamics generated in the experimental studies on cold flow could be incorporated and tested with against CFD simulations using either the Euler code or the volume of fluid code, and these simulations can be used to predict the influence of reactor scale on the hydrodynamics. There could be a pilot plant or demonstration unit. Typically, such a unit could be, say, a meter in diameter, and this could be used in part to validate the scale-up strategy and also to gain operating experience for the commercial unit. So combination of CFD investigations coupled with pilot plant or demonstration units could be used to develop the design and scale-up rules for the commercial scale bubble column slurry reactor for Fischer Tropsch synthesis. In the remainder of this presentation, I will focus on the CFD simulations and test the CFD simulations against cold flow experiments that are carried out in experimental studies with column diameters ranging from 10 centimeters to 1 meter in diameter. And on the basis of this, I will show CFD simulations of bubble columns of 6 meters and 10 meters in diameter. It will give you an idea of the importance of the reactor dimensions on the hydrodynamics of the FT reactor. I list here some of the key points of the scale-up strategy I'm proposing based on experiments in cold flow units coupled with CFD simulations. The important points to note are that the bubble column hydrodynamics is complicated by liquid circulations. The liquid circulations influence the rise of bubble swarms, and these are coupled because the circulations are induced by bubble swarms, and the rise velocity of the bubble swarms is influenced by the liquid circulations. Computational fluid dynamics ensures good housekeeping and is a viable alternative to empirical correlations for scaling up. Indeed, I would even argue that empirical correlations for scaling up bubble column slurry reactors are not to be recommended, and CFD is perhaps the only route to reactor scale-up. This is a tongue-in-cheek remark which states that CFD works best if you already know the answer you're looking for. What I'm trying to say is that you need to have an intuitive understanding of scale-up phenomena based on cold flow studies before you can trust your CFD simulations. Once you gain trust in CFD simulations, then only can you proceed to scale up. So qualitative insights are essential. Let's first have a look at an air-water bubble column reactor operating in the turbulent regime. You see we have the coexisting coexistence of large and small bubbles. The large bubbles rise predominantly through the central core region, whereas the small bubbles are evenly distributed over the entire range of the column. So in setting up the CFD simulations for an air water bubble column, we need to consider the existence of large bubbles indicated here as yellow, spherical caps, small bubbles indicated by these ellipsoidal shaped white bubbles here. The blue represents the liquid phase. So the Eulerian simulations for bubble columns are best carried out by considering small bubbles and large bubbles dispersed within the liquid phase. Precisely how this is done is discussed in the papers that I have mentioned right at the beginning. Let's look at Eulerian simulation results for a air water bubble column of 38 centimeter diameter, 2 meters in height. We will compare the Eulerian simulation results with experimental data, and these experiments were conducted in the 38 centimeter diameter column shown here in my laboratory in Amsterdam. The experiments were conducted by my former PhD student Ioana Urseanu, and the data I will present is from Chemical Engineering Science 2000. Let's look at the Eulerian simulations of the liquid flow as viewed from the top of the column. And I show you the animations showing the velocity vectors in the liquid phase. Please note that the flow in these 3D Eulerian simulation appears to be totally chaotic, and also they are not monotonic, and the flow directions change from clockwise to anti-clockwise with progression of time. These three snapshots here are at time 35.2 seconds, 37.7 seconds, 40.2 seconds from the start of the simulations. We note that at 35.2 seconds, the flow direction is in the velocity vectors are in this direction, whereas they change direction as time progresses. Here the velocities are pointed in a different direction. Indeed, when looking at the experimental column, we did not quite appreciate the switch in the in the flow directions. And only after the 3D Eulerian simulation results were available did we go to the top of the column to observe that indeed the flow directions change periodically with progression of time. Put another way, CFD simulations led us to have a better understanding of the air-water experiments in the 38 centimeter column. This graph presents the experimental data for the radial distribution of the liquid velocity along the axis of the air-water bubble column. These are shown by the red triangles. The blue circles are the corresponding experiments for a bubble column with Tellus oil as the liquid phase. The continuous lines are simulations using the 3D Eulerian approach. We note that the liquid velocity is upwards in the central core region, and close to the wall, the liquid velocity is directed downwards, and this downward liquid velocity drags with it the smaller bubbles downwards. So if we visually look at the bubble column experiments from the outside, we see small bubbles being dragged downwards by the liquid velocity profile. The liquid upflow in the central region has the effect of accelerating the larger bubbles up through the central core region. So CFD simulations allow us to have a proper housekeeping of the interaction and inter-influence, mutual influence of bubble rise and liquid velocities. The bubble rise influences the liquid velocity profiles, and the liquid velocity profiles in turn influence the bubble rise. We now consider the hydrodynamics of a bubble column of 1 meter diameter, 7 meters high, and we compare the experimental data for air-water system with CFD simulations. The experimental data are provided in a series of papers by Ange, and this is a review article published in 2006 that contains references to the series of experiments in the 1 meter diameter bubble column. We show now animations of 3D Eulerian simulations of a bubble column of 1 meter diameter, 7 meters high, with air-water system. We consider separately the liquid phase, the small bubble phase, and the large bubble phase. Let's have a look at the velocities of the liquid phase. We note that there is a tendency for upflow towards the center and downflow near the walls. If we now look at the motion of the small bubbles, they generally tend to follow in the same direction as the liquid phase. In other words, the small bubbles go up through the central core region and down the walls. We turn our attention to the large bubble phase. The motion of the large bubble phase is predominantly in the central core region, upwards through the central core region, and there is no downward motion of the large bubbles. We now compare the experimental data for an air-water bubble column of diameter 1 meter and height of 7 meters with CFD simulations. This graph compares the gas holdup as a function of superficial gas velocity. The red circles are CFD simulations, and the green squares are the experimental data obtained by Foray. In this graph, we show the axial component of the liquid velocity as a function of the radial distance coordinate. This is the center of the column. This is the wall, and the CFD simulations are shown by the red circles, and the green squares are the experimental data obtained by Foray. The data on the radial distribution of gas holdups for large bubbles, shown by the red circles, and the red circles are the small bubbles, and the green squares are the large bubbles. And we see that near the wall, we have a high proportion of small bubbles and practically no large bubbles. And at the center of the column, we have a very high proportion of large bubbles, and this proportion decreases to practically zero near the walls. So if we view the column from the sides, we only see small bubbles, and because of the downward velocity of the liquid phase, these small bubbles tend to be dragged downwards near the wall region. Since the Eulerian simulations tend to confirm the experimental data on gas holdup and liquid velocity profiles, we could use Eulerian simulations to understand the scale effects and the influence of increasing column diameter on the liquid circulations is demonstrated in the slide by means of Eulerian simulations for a 1 meter diameter column, shown here on the left, and a 4 meter diameter column. I plot here the centerline liquid velocity, and the centerline liquid velocity for a 1 meter diameter column is about 1 meter per second. The corresponding results for a 4 meter diameter column, this shows that the centerline liquid velocity fluctuates wildly, and the centerline liquid velocity is on average is about 1.5 meters per second larger than that for a 1 meter diameter column. Now, you need to time average the liquid velocity over long simulation times. Indeed, I will show the time averaged liquid velocities for a 10-meter diameter column, and those simulations were run for 3 months. Very, very expensive CFD simulations indeed. The scale effects for air-water bubble columns are summarized in a set of figures shown here. Let's first consider the centerline liquid velocity, time averaged. We compare the experimental data shown by the green squares with CFD simulations using the 3D Eulerian simulations shown by the red circles. The CFD simulations indicate strong fluctuations in the liquid velocity profiles, and therefore the estimations of the liquid velocity are subject to large error bars. In any case, we see that there is a strong increase in the centerline liquid velocity with increasing column diameter as we go from 1 meter, 2 meters, 4 meters, 6 meters, and 10 meters. As a consequence of the increase in the liquid circulation velocity, the axial dispersion coefficient is strongly influenced by the column diameter. Here are the experimental data for air-water system shown by the green squares. The red circles are the CFD simulations for the axial dispersion coefficient determined from tracer experiments in the CFD Eulerian simulations, and the triangles represent the axial dispersion coefficient for gas solid fluidized beds that are also strongly scale dependent. But it's interesting to note that the normalized axial component of the liquid velocity, where the liquid velocity is normalized with respect to the centerline liquid velocity, that has an almost a universal velocity profile that is practically independent of column diameter. So I have CFD simulations for 1 meter diameter column, 2 meters diameter column, 4 meter diameter column, 6 meter diameter column, and 10 meter diameter column, all collapsing into a single normalized axial velocity profile as a function of the radial distance coordinate. Due to the increase in the centerline liquid velocity, there is a reduction in the gas holdup with increasing column diameter. These are the CFD simulations shown by the red circles, and we have one experimental point for the 1 meter diameter column. These are the experiments of Foray. What we have learned so far is that the liquid circulation velocities can be as high as 2 meters per second in large diameter columns. And with this information, along with the fact that we have suspended catalysts in the FT reactor, these high velocities may lead to erosion of the internals, and this should be taken into account in the design of the internals for the FT reactor.